Welcome back to the worst day of your life. Have you ever wondered what kind of black magic are these incredible graphics, such as the one you're seeing right now? It's actually quite simple. I lied. First of all, the two most important parts of a computer are the CPU, which does math and other things, and the memory, which is a giant list of numbers. Screens work with pixels, which are a lot of tiny squares each with their own color, so the easiest way to do graphics is, you take the memory and choose a part of it to be a list of colors. So every once in a while it goes, I want that pixel to be this color now, and then it gets sent to the screen. Unfortunately, that's obnoxious, so modern graphics are a bit more complicated than that. Now we also have a GPU. A CPU can do pretty much everything, but it usually only does things one at a time, which is quite slow. Meanwhile, a GPU doesn't do much, but it does them hundreds of thousands of times simultaneously. But the CPU still has to talk to the GPU somehow. And that's where graphics APIs come in. There's a couple of them, such as DirectX and Vulkan, but we're gonna use OpenGL for this, as it's not too hard, and works on pretty much everything made after 1995. It is a C library though, so make sure you have a half-decent computer, a C compiler, electricity, and a copy of the book, The C Programming Language, 2nd edition, by Brian Kernighan and Dennis Ritchie. Come back to this video when you're done reading it. I'll wait. As all good things in life, we first need a window, as it's hard to draw when there's nowhere to draw. Each platform has their own uniquely cursed ways of doing that, so we're just going to use a library called GLFW to do that for us. Now we need a main loop, which is called that because it keeps running as long as the window is opened. It can run many times a second, maybe 60, maybe 144, or maybe 6000. Now we just clear the screen, so we can draw every frame from scratch, which is great because if you don't clear the screen, it looks really funky. You can choose any color, so I'm gonna use my favorite one, fresh brown poo. If we run this now, we just see the color of shit. Which means it worked. To draw something slightly more interesting, we need some triangles. Everything in 3D is made of a lot of triangles, as it's the simplest shape and the one the GPUs are optimized for. You just choose 3 points, called vertices, and OpenGL connects the dots. For more complicated shapes, you can add more triangles. So we send this data to the GPU, tell it how it's structured, and it won't work. In modern OpenGL, which is 15 years old, you're required to put this in a VAO, or vertex array object. A VAO is where you put your VBO, or vertex buffer object, which represents the vertex data when it's on the GPU. Do not mix them up. To draw our beautiful triangle, we just bind the VAO, and use this function. If we run this now, you'll see nothing. But don't worry, your PC isn't busted, or maybe it is, I don't know, I'm just a video on the internet. We need a shader, which is a program that runs on your GPU. Shaders are written in GLSL, which is quite similar to C, so you don't have to read another book. Our triangle goes through many steps. First it goes through a vertex shader, which decides on the final position of the vertices, we'll talk about that later, then OpenGL connects the dots, turns them into pixels, and then we can use a fragment shader to color the pixels. We don't have either, so our triangle is being drawn nowhere with the color of nothing. These shaders just tell OpenGL that our triangle is where it's at, with the color that it has. For this to work, we also have to change our mesh to have colors at each vertex too. If we compile, link, and then use the shader, which has a lot of steps you don't care about, you can now finally see a triangle. And if we change the mesh a little, we have a square. Except I lied. You weren't ready to handle the truth. We actually have another acronym, EBO, or Element Buffer Object. Why? To make a square, we need 2 triangles, and our current square defines the same 2 points twice, which is a waste of memory. And this gets much worse on more complex models, like a sphere. Instead we have 2 lists, a list of vertices, and a list of indices, which refer to a vertex. And similarly to how a VBO represents the vertices in the GPU, an EBO represents the indices in the GPU. Now we see the same square, but slightly more efficient. To celebrate this astounding technological achievement, let's do a bit more work, specifically textures, and an UI for testing. We'll get to 3D eventually. To get textures, you first need to load an image. As you may know, there are many image formats, such as PNG,
JPEG,
GIF, and the quite okay image format. Manually loading all of them would be obnoxious, so we'll use another library. STB. STB has a lot of features, such as STB TrueType for fonts, STB Image Write for making images, and STB Herringbone Wang, which is, You guessed it, a herringbone wang tile generator, but we're just gonna use STB image. After loading the image, you create a new texture, send the image data to the GPU, and well, use it. But OpenGL doesn't know what to do with it yet, so you have to change your mesh to also include texture coordinates, or UVs, which tell what part of the texture to use. It also works with points, so each vertex is a point in a 3D world, and a point in the texture. The shaders have to be changed too. The vertex shader now takes in the UV, but it doesn't need it, so it gets sent to the fragment shader, which also takes the texture through in uniform, which is a way to send things to the shader without having to change vertex data. Then the fragment shader takes whatever UV it has, and colors the pixel with whatever pixels the texture has. You can even mix it with vertex colors if you're feeling fancy. As for UI, you can make it all yourself, but that's gonna take a while. Instead we can use more libraries, either I'm GUI or Nuclear. I'm gonna use Nuclear because it's a bit easier to include into the project, but you can use anything, I don't care. I'm not gonna talk about how to use it, this isn't a tutorial, just use Google or something. It should look something like this. Now it's time to finally get into 3D. This involves a lot of linear algebra, so you could read another book if you want. Just know that the order when multiplying matrices matters, so A times B isn't the same as B times A. We're gonna use a library called linmath to handle matrices. We need 3 of those: the model matrix, which is where something is in the 3D world. This is also where you put rotation and scale, the view matrix, which is the camera, and the projection matrix, which is how you turn 3D into 2D, so you can see it in the screen. If you go into the great game known as Outside, you can see that things that are further away get smaller. That's called a perspective projection. You can also use an orthographic projection, which doesn't do that. In fact, pretty much all modern 2D graphics is done through an orthographic camera. Your life is a lie. Now multiply all of them together to get the aptly named MVP matrix, or model view projection matrix, which is named that because it's all of those matrices. Now you can send that to the vertex shader through in uniform, where it'll get multiplied by the vertex position. And would you look at that? A 3D square. Only problem is that we did all that just for it to look like shit. To solve that, we can add lighting. There are many ways to implement lighting, such as deferred shading, which is very fancy, and very out of the scope of this video, so we're gonna use something simpler. I won't go very in depth into this though, because my own implementation is questionable. First, make sure your mesh has normals, which is, you guessed it, an object, e.g. a line, ray, or vector, that is perpendicular to a given object. Then send that to the fragment shader, where the lighting is handled. As you can see from this stolen graphic, there's 3 components we're gonna use. First, ambient lighting, because even when it's dark there's still some light somewhere. That is not life advice. Then diffuse lighting, which controls how dark each face of a mesh is. And finally specular lighting, which just makes it a bit more realistic. Combine all of those and you get a cube, but fancy, cross-platform, and made entirely from scratch by you. Well, not you. You're probably just eating or something.
Sir, this is an Apple store.